This is Chapter 11, Section 6, the pH scale. In this section, we're going to learn about the pH scale. The pH of a solution is a measure of its acidity, which we know is determined by the concentration of hydrogen or hydronium ions in the solution. Experimentally, we can determine the pH several different ways. We can use a digital pH meter, like you see here in picture A. This measures the conductivity of the solution, which is due to those hydronium ions. Or we can use pH paper, like in picture B, or a solution indicator, like in picture C. This one is extracted from red cabbage. And the pH paper and the solution indicators both change color depending on the pH of the solution. We saw in a previous section that an acid is a substance that causes the concentration of hydronium ions to increase and the concentration of hydroxide ions to decrease. This means that the most direct measure of the acidity of a solution is just the hydronium concentration. However, this concentration can vary widely. Even for typical acid-base solutions, the hydronium concentration ranges from 1 molar for concentrated acid down to 10 to the negative 14th molar for a concentrated base solution. To make these numbers easier to work with, scientists have agreed upon a definition of acidity that compresses them down to the 0 to 14 pH scale that we're more used to. In this new definition, acid solutions have a pH of less than 7, bases have a pH of greater than 7, and a pH of exactly 7 is a neutral solution, such as pure water. If you recall that the concentration of hydronium and hydroxide are both 10 to the minus 7th for pure water, it can help you to remember the neutral cutoff value between the acids and bases. We'll see in a moment that this isn't just a coincidence. This graphic shows some familiar substances and where they are on the pH scale. You can see that many of the foods that we eat fall into the acidic range, while many household cleaners are more basic. Pure water has a pH of exactly 7, but drinking water can sometimes be as low as 5 or as high as 9 or even higher, depending on the source and the minerals and electrolytes dissolved in it. Our bodies can actually tolerate a relatively wide range of pH, but one thing to keep in mind is that acidic solutions can dissolve or corrode some metals. This means that if the water from your faucet has a very low pH and it traveled through miles of municipal pipes to get to your house, it could potentially be contaminated with heavy metals or other dangerous substances. In this case, it's not the acidity of the water that's the problem, but the other things dissolved in it. Before we get to the exact mathematical definition for pH, let's just review a few other ways that we can characterize different solutions or substances based on the pH or the concentrations of ions in them. So the first one here is HCl, that's hydrochloric acid, with a pH of 1.5. Now, obviously, hydrochloric acid is going to be acidic, and that matches with this given pH, which is 1.5. That's less than 7, and so obviously this is in the acidic range. The next example is pancreatic fluid, where they give the hydronium concentration of 1 times 10 to the minus 8th molar. Now, keep in mind that every solution has both hydronium and hydroxide. Just because they're telling you that the hydronium concentration is some number here doesn't mean that this is an acidic solution. In fact, this concentration of hydronium is less than 10 to the minus 7th, which is the concentration it would have in neutral water. That means that this pancreatic fluid has less hydronium than neutral water, and therefore this is basic. For C, we're just looking at the pH of Sprite soft drink. It has a pH of 3.0. This is less than 7, and so therefore this is acidic, as most soft drinks are. A pH of exactly 7.0 we know is neutral. For E, it tells us that there's a solution with a hydroxide concentration of 3 times 10 to the minus 10th molar. Now again, just because they're telling us that there's some hydroxide in this solution doesn't mean that it's basic. This number is less than 10 to the minus 7th molar. So this solution has less hydroxide than a neutral solution. Therefore, this is actually acidic. Same thing for F. They tell us hydronium, but the concentration of hydronium that they give us is less than it would be for neutral water, 10 to the minus 7th, and therefore this is a basic solution. So you can't just look at whether the number is greater or less than 10 to the minus 7th, you also have to know exactly which ion you're talking about. Now we're going to see the actual definition for the pH. we know that the pH is meant to compress down the wide range of hydronium concentrations to a more manageable scale, and it does this by using a logarithm. pH is a logarithmic scale for the concentration of hydronium, and the definition is that the pH of a solution is equal to the negative logarithm of the hydronium ion concentration. Now, this is a base 10 logarithm, so make sure that you're using the correct key on your calculator and not the natural logarithm or something else. And also don't forget this negative value. Since the concentration values often have negative exponents, this negative value makes all of our pH values positive rather than having to work with negative values consistently. When you're calculating the pH of a solution, you can generally get a rough estimate by looking at the power of 10 in the concentration of hydronium. So if the concentration of hydronium is 1 times 10 to the minus 2, the pH is going to be exactly 2. If the coefficient changes, but you still have a power of negative 2 in the concentration, the pH is going to be close to 2, but a little bit lower. Here you can see for all these examples, you have 10 to the minus 2 as the power of 10, and just varying coefficients for the concentration, and all of these pH values are within 1 pH unit of 2. Now this depends on making sure that you have the hydronium concentration expressed in proper scientific notation with a coefficient between 1 and 10. This might not always be the case when you're doing a calculation, so when you're first starting out, you should be careful with these kinds of approximations. When we're dealing with significant figures for pH calculations, we need to use different rules than for multiplication, division, or even addition, subtraction. The logarithm has its own set of rules. So the rule in this case is that the number of decimal places given in the pH value has to be equal to the number of significant figures in the coefficient for the concentration. So in this example, if our concentration has 2 significant figures in the coefficient, then our pH value should have 2 decimal places, 2 digits after the decimal. Remember from the last slide that we can also estimate this ones place from the power of the 10 in the concentration. Just keep in mind that it's not going to be exactly the same unless the coefficient is exactly 1. Now, since pH is a logarithmic scale, changing the pH by 1 unit actually corresponds to a 10-fold change in the hydronium concentration. The negative sign in the formula, remember, means that we're going to take negative powers of 10 in the concentration and get positive pH values. This also is what inverts the pH scale so that lower pH values correspond to higher concentration values and therefore more acidic solutions. What that means is that if you have a pH of 2, this is a more acidic solution than a pH of 3 by a factor of 10 in the hydronium concentration. So if our pH 2 solution has a concentration of 1 times 10 to the minus 2 molar, then pH 3 is going to be a concentration of 1 times 10 to the minus 3 molar. It'll be 10 times less hydronium because we're going up and therefore the acidity is decreasing. If we go up by another pH unit to a pH of 4, the concentration again drops by a factor of 10, and we have 1 times 10 to the minus 4th molar hydronium. This example is a relatively straightforward question about calculating pH from a solution with a known concentration of hydronium. The question says aspirin, which is acetylsalicylic acid, was the first non-steroidal anti-inflammatory drug used to alleviate pain and fever. If a solution of aspirin has a hydronium concentration of 1.7 times 10 to the minus 3 molar, what is the pH? To answer this question, you really just need to remember the definition of pH. We know that the equation is that the pH equals the negative log of the hydronium concentration, H3O+. Since they gave us the hydronium concentration directly in the problem, we can just put that into the logarithm and we get the pH is the negative logarithm of 1.7 times 10 to the minus 3. We can leave out the unit. pH doesn't really have a unit, so we don't need to worry too much about that. When you put this into your calculator, most calculators you'll put in the concentration first and then hit the log key and then don't forget to take the negative sign. The output of your calculator in this case would be 2 0.76955179 or something like that, depending on how many decimals your calculator shows. And then we have to think about significant figures. The coefficient of the concentration here has two significant figures, and so we really only need to keep two decimal places in the pH. Since this is a 6 and this next digit is a 9, which is greater than 5, we're going to round the 6 up to 7, and so this pH is really going to be 2.77. Again, there's no unit for pH, it's just a pure number. This is another straightforward example. It says find the pH of a solution with a hydronium concentration of 4.0 times 10 to the minus fifth. So once again, we just need the formula for pH. pH equals negative logarithm of H3O plus. We put the concentration that they gave us directly into the formula, and so we're looking for the negative logarithm of 4.0 times 10 to the minus fifth. If you punch this into your calculator, you should get pH equals 4.3979400009. At least that's what my calculator shows. And again, we would round this to two decimal places because there's two significant figures. So we would keep the 39, but since this is a 7, we're going to round this up. Now we round it up to 4.40. Make sure you keep this 0 in because it is significant according to this rule that we just said. Just because you're rounding 39 up to 40 doesn't mean that you drop that 0. One other thing to keep in mind about these problems is what we said about estimating the pH based on the power of 10 in the concentration. We can see here the power of 10 is negative 5. We drop the negative sign, and we find that 5 is indeed pretty close to our pH value. So your pH value is, generally speaking, going to be within 1 pH unit, usually below the power of 10 in your concentration. Of course, we also want to be able to reverse this calculation and figure out the hydronium concentration from the pH value of a solution. If you know how to deal with logarithms, you might be able to invert the previous pH equation and get this answer, but we're not requiring you to do that, so we just give you the formula for this step. The hydronium concentration is 10 to the power of the negative pH of the solution. So for whole number pH values, you get an integer exponent for 10. You can assume the coefficient is 1 or 1.0, depending on the significant figures, and then you're pretty much done. For any pH that's not a whole number, however, you're going to get a decimal power of 10, and then you would really need to put that into a calculator in order to get proper scientific notation. Usually this is done with something like a 10 to the x key on your calculator, which is sometimes buried in a secondary function. Refer to the manual for your calculator if you're not sure how to do this, or come see me and I can help you figure it out. Here's an example of that kind of problem where they give us the pH value and we need to find hydronium concentration. So the problem says determine the hydronium concentration of a solution that has a pH of 3.42. So again, referring to the previous equation, we know that the hydronium concentration, H3O plus, equals 10 to the negative pH. Since our pH is 3.42, that's what goes into the exponent, and we find that the hydronium concentration is 10 to the negative 3.42. Don't forget the negative sign, it's very important. Now, again, this is not an integer exponent, and so we're not done. We have to actually put this into a calculator, and we end up with a concentration of hydronium, which is equal to 3.801893,963, and then times 10 to the minus fourth. Okay? And since we're dealing with a concentration, by the way, the unit becomes molar again. All of these concentration units will be molar, capital M. Now, of course, we don't want to leave all these decimals in here, so we have to think about significant figures. If we were going from concentration to pH, we would take the significant figures in the concentration unit and make them the number of decimals in the pH. Here, we're starting with the pH, so we need to make the number of decimals the number of significant figures in the concentration unit. So 2 decimals in the pH tells us that we really only need to keep 2 significant figures in this coefficient. So the correct answer here would really be the hydronium concentration equals 3.8. Since this is a 0, we don't need to round it up. We can just drop the remaining digits. So it'll be 3.8 times 10 to the minus 4 molar. Again, depending on your calculator, the output can sometimes be confusing if it's in scientific notation like this. So make sure you refer to your manual to find out how your calculator displays scientific notation in powers of 10 in the output.